I believe this is on page 13 of your unit handout, isn't it? So we're looking today at what's called the factor theorem. And you know, I'll mention this now because later on, hopefully it will make sense. The factor theorem is really a specific situation with the remainder theorem. It is the remainder theorem, but only under certain circumstances the remainder theorem becomes the factor theorem. What we're going to be focusing on today is factoring polynomials. So if you look at any of the polynomials that are factorable, whether it's degree 2, which you know how to factor already from last year, degree 3, which you don't yet know how to do, degree 4, degree 5, degree 6, degree 7, at the end of today's lesson you will know how to factor those polynomials. So that's the goal, and we're going to be along the way learning the factor theorem. So to begin with, as a warm-up, I'm giving us a polynomial. It's 3x cubed plus 8x squared plus 3x minus 2. And I want you to find the value of the polynomial when x is negative 1. What does that mean? It means that we have to determine p of negative 1. Notice I'm taking the liberty here, everybody, of just calling this p of x. We can always do that. It doesn't have to say this is a polynomial function, but I can treat it as a polynomial function in order to wrap my head around the things that we're trying to do. So what does that mean? It means that I need to put in negative 1 for x, and although you could certainly load that polynomial function of x into your graphing calculator for y1 and go to your table, this is not a difficult task. The negative 1, when I raise it to an exponent, will either give us negative 1 or positive 1. It depends on whether the exponent is odd or even. Negative 1 cubed will be negative 1. Negative 1 quantity cubed will be negative 1 because it's negative 1 times negative 1 times negative 1. Negative times negative times negative is negative. So the first term of our evaluation will be negative 3. The second term will be positive 8 because negative 1 quantity squared is 1, and 1 is positive, times 8 is still positive. 3 times negative 1 is negative 3, and then we have minus 2. Capiche? Okay, so what does that equal? Well, whenever I add numbers together, I always like to add all the negatives together and add all the positives together and add a positive and a negative. And when I add the negatives together here, I get negative 8. You can add them however you want. I don't care. But I get negative 8 plus the 8, I get 0. And that's significant. The remainder theorem, and I'm getting a little bit ahead of myself. We're going to answer this formally by writing some things down, but I want to explain why the factor theorem, which we're learning today, is really the remainder theorem. Okay? Just briefly. The remainder theorem says that when we divide this polynomial by x plus 1, right? Just think about this for a second, that if this is p of a, that means we can think of this as being dividing by x plus 1. We get a remainder of nothing. We don't have a remainder when we do this division. Even though there's no division happening, I'm saying if we did divide by x plus 1, and I said, what's the remainder? You do this and you go 0. Right? Now, why is that significant? Well, it tells us that x plus 1 has to be a factor. Can somebody give me a factor of 24? What's a factor of 24? 6. Why do we know 6 is a factor of 24? Because 24 can be written as 6 times 4. Exactly. There's no remainder. Or, to turn it around, when I divide 24 by 6, I get 4. I don't get 4 with some leftover stuff. This is actually the mathematical definition of what a factor is. It's something that divides the dividend without remainder. So, to summarize all this, and the logic is a little tricky, but if p of negative 1 equals 0, then when p of x is divided by x plus 1, the remainder is 0. And I'm rolling through my head exactly how to complete this thought, but just verbally, that's the textbook definition of a factor. When you divide something by a factor and get a remainder of 0, it's because it's a factor. Okay? Only factors divide to get a remainder of 0. Now this goes back to the 26 over 3, I think, that we started with yesterday. 3 is not a factor of 26, because when you divide 26 by 3, you get a remainder of 2, I think it was. Yeah, 8, remainder 2. Whereas 6 is a factor of 24, as a different example, because when you divide 24 by 6, you get exactly 4. You don't get 4 point something, you don't get 4 remainder something. Are you with me here? So if you can find a value of x, this is kind of how we're going to be factoring in a way. If you can find a value of x that makes a polynomial equal to 0, then you will have found a factor of the polynomial. Now be aware, this only works for factors. I don't even think I want you to write this down, but we're talking here about factors of this form. All right? We're not talking about, so we're talking about factors like x plus 2, x minus 3, even x, where a is negative 2, a is positive 3, a is 0. We're talking about this rule working for this. But you do not have a rule for factors like this, and you're not going to get one. You're not going to get a rule for factors like that. It turns out there is a rule, but we don't deal with it. Here's the problem. When I said at the beginning of the class, we learned today how to factor polynomials, these polynomials will contain these factors. But what you're going to do is use our skills we learned today to factor out all of these factors of the x minus a form until you're left with something that will contain potentially these factors on the right, but you'll factor it like you're in grade 11. You'll be down to a quadratic at that point in time. Speaking of which, use synthetic division to find the result of dividing the polynomial by x plus 1. Well, that's pretty easy. I say speaking of which because we're in the process of factoring this now, and you'll see how this all comes together in a second. 3, 8, 3, negative 2. We put the 0 of the binomial here, bring the first number down, and we're ready to roll after we double check to make sure that we've written everything correctly. 3, 8, 3, negative 2. Always check to make sure that you've got every degree represented, and make sure the degrees are in the right order, because sometimes, just for kicks, we might write this as 3x cubed plus 3x plus 8x squared. We might switch the order. I think it's written correctly, so we put a negative 3 here because that's the product, and we add and get 5. Negative 1 times 5 is negative 5. Add, you get negative 2. Negative 2 times negative 1 is positive 2. This is always a nice thing because it reinforces the idea that what we suspected was a factor really is a factor. This is a good thing. That's what we expect. Okay, it's a 0, but you can put a happy face on it, or you can just say, that's it, that's good. What does this mean? Well, let me ask you a question. If I told you that we wanted to factor 255, and you looked at that, and if I were looking at it, I'd go, well, 5's a factor. So what would I do to factor it? I would take my calculator or my brain and I would divide 255 by 5. Can you do that for me, please? I should get 51. What does that mean? It means that the original thing is equal to the thing that we knew was a factor times the result of the division, right? And now you can go, well, how does 51 factor? And it turns out it's 17 times 3. It's not a prime number, it's 17 times 3. So what you would do is you would say, well, I've extracted that 5. Now how can I break the 51 apart? And I go, it's 17 times 3, or 3 times 17. Are you with me on that? So if I said to you, factor 3x cubed plus 8x squared plus 3x minus 2, and I told you, and I did in this question indirectly, that x plus 1 is a factor, I told you that. I'm not going to tell it to you in the next example. We've got to find it. Then that means we can write this polynomial as x plus 1 times whatever the quotient is when we do the division. And that's going to be 3x squared plus 5x minus 2. Correct? Just like if I said 5 was a factor of 255, you'd divide it to find out the other factor, and then you would continue the factoring process. And what we've done now is extracted this linear factor of x plus 1 out of a cubic polynomial, so the other factor is quadratic, and we can do that. We know how to do that. For any of you that I taught math to at earlier grades, I never used the method of decomposition for factoring these things. And the fact that some of you just looked at me and gave me the stink eye, meaning you don't even know what I'm talking about, is maybe good. Because I don't think the method of decomposition is something you should be doing at this level. I think it's too time consuming and it doesn't even really make sense. How many of you know what I'm talking about? Not how to do it, but how many of you, in the back of your head, you have this, okay, we were taught something called the method of decomposition. If I were to ask the people who do remember that, do you remember how to do it? The number of hands probably starts to fall. We use trial and error here. And my thinking is that if I give you two binomials to factor, if I give you two binomials to multiply together with FOIL, it shouldn't take you much more than 10 seconds to see what you get. So combining that skill with a little bit of logic, and here comes the logic, makes this easy. The fact of the matter is this has to be a 3x and this has to be an x. That's the only way you're going to get 3x squared out front, right? And the fact of the matter is these two numbers in here have to multiply to give the negative 2. One's going to be positive, one's going to be negative. So here's where the trial and error comes in. I'm just going to put, I said 1 and 2 in that order. That's the order I'm going to write them down. I can see right away, I think this is going to yield a correct answer. And what I do is I do this. When I multiply 3x by x, do I get the 3x squared? Yes. When I multiply the 1 by the 2, do I get the 2? Forget about the negative. Yes. You don't need to check that, because you put those numbers precisely for that reason. What you need to focus on is what the outer is and what the inner is in your foiling. My outer is a 5x currently. My inner is a 1x. Sorry. Occasionally, my brain does that. The outer is 6x. 2 times 3 is 6. My inner is 1x. Can I combine those to get positive 5x? And the answer is yes, if this is positive and this is negative. And what I'm taking the opportunity to do here is do a very quick review of factoring quadratics. We're done. That's factored. If you want to multiply it all out, feel free, but we're not going to do that at this level. This is a factor that you could have discovered with the factor theorem, and this is a factor that you could have discovered with the factor theorem. You don't quite know how yet, but it's possible. The middle factor that I've written there, the 3x minus 1, is something you could never extract with the factor theorem. For those of you that are wondering, the value of x that's the 0 for that middle factor is 1/3. If we set that equal to 0 and solve it, we discover the number that makes it 0 is 1/3. P of 1/3 would give you 0, but you would never think to look at that. All right. So we've just learned how to factor, with one exception, and we're going to get to that in just a minute. Notice that, and I'm repeating myself here, but that's okay. Notice that since the remainder of the division was 0, the divisor must have been a factor of the polynomial. And that's the goal today, and it's the most important thing. If you can find a number that makes the polynomial 0, a number for x, then you will have discovered a factor. Okay? Can you apply what you already know about the remainder in the division of a polynomial to express that polynomial in factored form? I believe on my note package it just says 4. That's the only reason I've highlighted it. And this whole idea that this warm-up has taught us is summarized at the top of the next page of your handout. It's called the factor theorem. If x minus a is a factor of a polynomial, then p of a will have to give you 0. Because when you divide by x minus a, p of a is the remainder. But if x minus a is a factor, the remainder is 0. Do you see how this is just kind of going around in circles here? We're just saying the same thing over and over again. I could say if p of a is equal to 0, x minus a is a factor. Because if p of a is equal to 0, that means the remainder is 0 when you divide by x minus a, which means it's a factor. It's just the remainder theorem as long as the remainder is 0. So here's how things change. Oh, one more thing. This is really important. You may not notice this, but I'm telling you if x minus a is a factor of the polynomial, a has to be a factor of the constant term of the polynomial. So let that sink in your brain what I'm saying. If a polynomial ends in plus 30, I'm telling you any factor of the form x minus a has to be a factor of 30. Why? Well, let's say we had these 4 factors multiplied together. I taught you 2 lessons ago, that's factored form, this is going to be expanded form, that if you multiply the highest degree terms together, you get the leading term of the polynomial written in expanded form. You with me? And if you multiply all of the constant terms from each factor together, you get the constant term. And you get other stuff, okay? Filler. But you've got these 2 pieces of bread and then the stuff in between, which we don't really care about. Well, I want you to notice that these factors are factors of the form x minus a. And that's what we want to focus on. We could look at the other factors, but I don't care. I want you to notice that each value of a is a factor of 30. What is the value of a in x minus 2? 2. 2 is a factor of 30. And I hope it makes sense that 2 is a factor of 30 because we got 30 by multiplying 2 by other stuff. When you look at the factor x minus 1, the value of a there is 1, and 1 is a factor of 30. These numbers here are also factors of 30, but they don't help us because they're not x minus a situations. So a is always a factor of 30. Okay, so factor this polynomial. Now, we're going to be cheating a little bit on our calculator, but I want to keep the cheating to a minimum right now. Okay, what's going to happen is eventually, and it will be tomorrow, I'll show you how you can just factor it on your calculator. But I don't want us doing it that way, and I'll explain why in a bit. Factor the following. Well, you don't know how to factor a cubic polynomial, but if we can come up with a linear factor and divide it to get a quadratic factor, we can finish it. So what we are going to do is say that this is a list of potential zeros. What does that mean? It's a list, we're going to generate a list here of numbers that could make the thing 0. If 5 makes that thing 0, and it won't, then x minus 5 will be a factor. But we have just learned that all of those factors that we care about, those x minus a's, have a's that are factors of the constant term. Which means, and I really don't want you to write this down, I suppose you could if you wanted to. I could write potential factors. I don't. I'm going to write it here and then erase it. Potential factors would be all of these. Would be x plus 1, because negative 1 is a factor of negative 6. Would be x minus 1, because 1 is a factor of 6. Could be x plus 3, because negative 3 is a factor of 6. You get my drift here? Well, all I'm doing instead, I think this is not necessary. You can get away on a written response with this and just say, those numbers. There may be other numbers because of those other weird factors that are not x minus a's, but these are the integral potential zeros, the integers. So imagine that this is a written response question, and you've explained that I'm looking at potential zeros.
Our notebook says minus 7x, not 7x squared.
Your notebook says minus 7x?
Yeah.
Let's get back to my point here. You understand that the reason these are potential zeros is because they would correspond to factors of the form x minus a, and all of these numbers are factors of the constant term. Okay. So here's where you kind of cheat the system. You're writing a written response, you've kind of set this up, and now you're going to play dumb. You're going to find one of the numbers on your calculator. You're going to put in for y1 this polynomial, and you're going to go down the list until you see where it's equal to 0. Okay? You're not going to say this is what I did, because you're solving this algebraically. And by the way, that's what I had done. Yours is already in there, right? So everybody in y1 put in x cubed minus 7x minus 6. And just humor me. Follow along very carefully here. Give me 1 second to get my calculator over there. What I would like you to do, and by the time we're done with this lesson, you don't need to do this. Set up your table to go second window to go table set, and make sure it's on ask. Okay? Let's just pretend we're still learning, and I don't want you to get ahead of me and cheat too much. I don't want you to find all of the factors using your table. I want us to find one of the factors. If you find them all and write the answer, you won't get full marks. So I go to my table and I enter a 0. Now I have some other stuff in here. A potential 0 is 1. I'm going to put 1 in. I do not get 0. That means I can strike x minus 1 from my list of factors. X minus 1 is not a factor. But what if I use negative 1? I get 0. So here's where I say you're cheating the system and you're playing dumb to the marker of my unit exam, which would be me, or of the diploma exam, which is somebody in Edmonton. You go, let's try, I don't know, let's try x equals negative 1. Okay, do you get my drift of what we're doing here? And the markers know you know, right? I don't think you want to play so dumb that you're going to say, let's try 1 and waste your time showing that it's not a factor. So you go negative 1 cubed minus 7 times negative 1 minus 6. And you say, oh, that's equal to 0. You don't even need to check, right? Because you just did on your calculator. And then you say, x equals 0 is, x equals negative 1 is a 0. Therefore, 3 dots like that means it follows. Because of that, the following is true. X plus 1 is a factor. So how do we proceed? Just like if you knew 5 was a factor of 255, you divide to find out what the other factor is. We're going to take this polynomial we started off with and divide by x plus 1. And you're going to get quadratic because we started off with a cubic. So it was 1x cubed, 0x squared, negative 7x, negative 6. We put the 0 of the factor we're dividing by. And again, our internal check here, everybody, to make sure we're consistent, or our consistency here, is that we have to get 0 there. Bring down the first number. Multiply, add, multiply, add, multiply, jackpot. We get 0. And that means that this factor of x cubed minus 7x minus 6 is x plus 1 times x squared minus x minus 6. And just to make sure, that's where I'm getting the x squared minus x minus 6 from. And factoring that is child's play. It's not even a trial and error thing because the coefficient of your quadratic term is 1. So it is x plus 1. What two numbers multiply to give negative 6 and add to give negative 1? Negative 3 and 2. Which leads me to the point that if you just wanted to know what the factors were, and it wasn't written response. I don't know if I guess I'll explain it. How many of you see that since this is 1, the coefficient of the leading term is 1, every factor has to be an x minus a? Because it's got to be x times x times x. So if you're starting to put the pieces together here, we could have factored this looking at the fact that that's a 1, set your table up to be on automatic, starting at 0 and going up by 1, and find the 3 zeros. It's not always going to work, though. Okay, 3, so x minus 3 is a factor, negative 2 and negative 1, so x plus 2 and x plus 1 is a factor. We're going to run into situations where you can't do that, though. And it's when you have one factor that appears more than once. All right, let's try another one. Whew. Got a little lightheaded for a second there looking at that. Can you make sure that's the same as the one in your handout? Okay, we have to find a 0 that's a factor of 24 or negative 24 so that we can perform synthetic division by the corresponding factor to get a degree 3 factor. And then we have to repeat the process with the degree 3 factor to turn it into a degree 2 factor. Are you with me here? And I used to say for years, and I don't think you'd ever be given a degree 5 to do on a written response. And last January, not this past January, but the January before, surprise, opened up the diploma exam, algebraically factor the following degree 5 polynomial. So if it were degree 5, you'd extract 1, 2, 3 linear factors and factor the rest. I'm not going to show all the work here. I'm just going to write potential zeros. You would write them out if it were a written response. Will be factors of 24. And the most efficient way to find those factors is to load this into your calculator and go to your table. Or those zeros. So 5 x to the 4 minus 13 x cubed minus 14 x squared plus 52 x minus 24. I mean, I know you know. If you actually tried to put numbers in and crunch all those numbers, you're just wasting your time. So it's a long, arduous task. Sure, I've got that in right. and let's play real dumb here. I don't want to write everything down, but right now my table is on automatic, so I should be able to find more than one, right? Negative 2 is a 0. Negative 2 is a 0. 2 is a 0. I've got two zeros, and because it's degree 4, I have to extract two linear factors. Well, there they are. X plus 2 and x minus 2. So what I do is I say, we'll start with this one. And we are in total learning mode here, and I have to find ways with the shortened classes to cut corners. You would write 5 times 2 to the 4 minus 13 times 2 cubed minus 14 times 2 squared plus 52 times 2 minus 24 if it were a written response. And then you would, again, play dumb and go, it equals 0. Well, that's good, because that means this leads to x minus 2 is a factor. So let's factor it out. Just like factoring out the 5 from 255 involves division, we're going to do the division here. We have 5x to the 4, negative 13x cubed, negative 14x squared, 52x, negative 24. I can't see that it matches. Can you confirm I wrote the numbers down correctly for me? Good. Our 0 is 2. And once again, I used the word consistent earlier. That's not what I meant. As a kind of internal double check, it's pretty hard to make a mistake if you've entered it into your calculator like we have. But as a double check, we have to get 0 for a remainder. And if you were writing a written response, it might be noteworthy to draw an arrow there and say, see, the remainder is 0, so it is a factor. That might garner you a couple of extra points in the marker's mind. Bring down the first number. Multiply. Now, I might have mentioned this in the last lesson. I just switch into autopilot. I can't help myself. Be very careful here that you multiply and add correctly. Although if you don't get 0, you'll know you've made a mistake. Gives me negative 3, multiply. You know, when I start to get to here, I start to get a little worried. Like I start to second guess myself because I don't know how that's going to turn into 0. Just be patient and calm and see where it leads you. I multiply these and get negative 40. I add 52 and negative 40, it gives me 12. Now I'm starting to be a little more relaxed. It works. So what you're going to do now is say that the polynomial is x plus 2 times 5x cubed minus 3x squared minus 20x plus 12. And then you're going to do this. You're going to, it's not really that you're playing dumb. You're demonstrating to the marker that you know what's going on. We're no longer talking about factors of 24. And because you could have the same 0 that appears twice, like maybe 2 is still a 0 of this other thing. It isn't. Well, I shouldn't say that. I shouldn't say that. But there could be what we call multiplicities, where you have the same factor occurring more than once. You do not necessarily want to just go back up and look at the same polynomial. So to make this point, actually, I'm going to go into y and put in this polynomial now. I go to my table. This is all behind the scenes. And look at that. 2 is still a 0. And I've constructed this question this way intentionally. 2 is still a 0. So you could say, in this, P of 2 is equal to 0. What does that mean? It means there's another factor of x minus 2. And you wouldn't know that if you continued to look at the original polynomial in your graphing calculator. All you would see is, oh, 2 is a 0. But it's a 0 again. So I am now going to take this polynomial of 5x cubed minus 3x squared minus 20x plus 12, and I'm going to divide it by x minus 2. So I put the 0 here. Oh, I wrote this down wrong, didn't I? Thank you, Noah. That should be x minus 2. X minus 2 means you have a 0 of 2. Nobody's correcting it, so you wrote down x minus 2 the first time, I think. I didn't. Okay. So I bring down the 5 again. We'd better get 0 here, and we will. 2 times 5 is 10, and there's no need to write the x. I add the 10 and the negative 3 and get 7. 2 times 7 is 14. I add those two numbers and get negative 6. Times 2 is negative 12. And again, I'm happy with that outcome. So what does that mean? And then we had that degree 3 polynomial, but we factored out of that a further x minus 2. I want to go back and check something here. I want to make sure that I did in fact write up here that x minus 2 is a factor. And then we have 5x squared plus 7x minus 6, which we factor. It's got to be a 5x and an x. It's got to be a 3 and a 2. Pretty sure that does it. By the way, another comment on the cheating thing. I knew it was x plus 2 because negative 2 gave me 0 in the calculator. So we're done. What we're going to be learning tomorrow, just so you know, is there's a way to kind of use things we've learned about the leading term and the constant term and where they come from in the factors and your graphing calculator to factor most polynomials just on your calculator without writing anything down. Most, not all. All right, we have one more example to do here. Example number 2. I feel as though I really don't need to include an example like this in this lesson because it's identical to an example from Friday, except that rather than me telling you you divide by a binomial and you get a particular remainder, I'm telling you that the binomial is a factor. What this means, everybody, is that when you divide by x minus 4, the remainder is 0 because it's a factor. Are you with me on that idea? Well, what that means then is that P of 4 is equal to 0. And we're back to the question that kind of what we did when Joanna asked her question at the beginning of class from last week's work, that we can think of this as a missing parameter and the 4 and the 0 as an ordered pair. When I put 4 in for x, that whole thing has to equal 0. And then I can solve for k. So I'm going to have 2 times 4 to the 4 plus k times 4 cubed plus 19 times 4 squared plus 10 times 4 minus 24, and this is going to be equal to 0. And I'm going to double check all of my entries and coefficients and all of that. 2 times the input to the 4, k times the input cubed, 19 times the input squared, 10 times the input, and 24. So I'm going to do some mental math here. You've got calculators. I want you to double check to make sure that the numbers I'm writing down are correct. confident on that. Can somebody figure out what 19 times 4 squared is? No? Again, I don't know if I've mentioned this. I tend to do mental math, and I'm being sincere, with 304. Wow, how did I get... I tend to try mental math on my own. Wow, what was I thinking? 20 times 16. Oh, I thought 20 times 16 was 3,200. I know it's 19, but I took something away. 304. I tend to do mental math to try to keep my brain sharp. So now you add all these numbers together, 512, 816, and another 16 is 832. So I get 64k equals negative 832, am I right? So k is equal to whatever negative 832 over 64 is, and I couldn't be bothered. 6, maybe 13? 13? I didn't do the division, I just kind of estimated. So k is equal to negative 13. So the remainder theorem is used primarily to factor polynomials. And what you do is you chip away at them until you get to a degree 2. There's also this application here. I wouldn't try to do this by reverse engineering some kind of synthetic division, this question. Some of you will want to. You'll think that that's the way to go, but it gets very unwieldy. So that's the lesson for today. You've got 11 questions, 12 questions it looks like on pages 15 through 17 that I would like you practicing. You've got about 12 minutes or so here. Yeah. Maybe closer to 15, but you have a little bit of time here to work on these. Tomorrow we will look at part 2 of the factor theorem, where we kind of really cheat the system and just say, what if you just want to know all the factors? How can we do that on our calculator? So get to work, please. I will come around and help you out. I just have to do my attendance first.